Hello and welcome back to BitLearn series on modern operating system design. So if you have missed the earlier episodes, we covered why operating systems exist. We looked at how they are structured, and in the last episode we looked at how processes and threads they kind of create the illusion that many programs can run at the same time. But that illusion immediately raises a deeper question. If there are processes that are ready to run and only one CPU core is available, who gets the CPU, when and why? So that decision is made continuously by the operating system millions of times per second through something called as CPU scheduling. So in this episode we will look at how that decision is made, from early scheduling ideas to the intuition behind the modern schedulers. So if you haven't seen the earlier episodes, I would strongly recommend starting there. This series is designed to build layer by layer, just like the operating system itself. So with that, let's get started with this episode. So in this episode, we are going to look at CPU scheduling. So it basically talks about who gets the CPU, when, and why. So a modern computer feels very fast because the operating system pretends that many programs are running at the same time, even when there is only one CPU available. At the center of all this illusion is there is a concept called CPU scheduling. So you basically decide how much CPU will be allotted to each process, each application. So every runnable process wants the CPU now. So if you have a clock or if you have an alarm running, it needs the CPU now. It needs to do its calculation of moving the minute hand. The operating system must decide which one runs next. So after the clock is done, who should run next? Is it the webcam application or is it my speaker? It's hard. So how long does it run? I don't even know as the operating system. When does it stop? So this decision happens millions of times per second. And CPU scheduling is not just a technical mechanism, it is a set of choices that the OS has to make sure that it is fair, responsive, and efficient to the user. So let's look at the problem first. What exactly is the scheduling problem? So at its simplest, the CPU scheduling answers just one question. When the CPU is available, which process should run next? That is basically the scheduling problem. So the difficulty lies in the fact that the operating system does not know, it basically cannot predict the future. It does not know how long a process will run, whether it is interactive or compute heavy. So if I give the CPU time to, let's say, this fictional clock application, does it take over the CPU entirely, do all its job, and it's never going to give the processing back for, let's say, the browser? So the browser will hang because the clock took over the CPU. Yet the OS must decide quickly, repeatedly, and under constant load when, how, and how much CPU does each process get. So that is the problem. So every scheduler is therefore trying to make a compromise, but a well-established compromise. So now let's look at what was the earliest forms of scheduling that was used. So the early systems, they kind of experimented with cooperative scheduling, where the author of the clock would be given a lot of freedom to use the CPU, and he decides when he wants to release the CPU for another application like the browser. So if I am the browser's developer, I get the full CPU. Cooperatively, I decide, okay, I have loaded a page. Now the user is just reading through the page. I'll release the CPU to some other application. So this was the initial attempt. It kept running until voluntarily somebody gave up the CPU or any resource for that matter. So this model is quite simple and efficient, but it is dangerously optimistic, because if I am the author of the clock, I believe I am the most performance intensive and efficient application. I believe I need the CPU every second because I'm going to update my clock every second. If I am the browser, I decide I need the CPU every second because I have a lot of work to do. I'm going to show a web page, I'm doing some animation here on the page, I'm trying to make some network calls. So this whole idea of cooperative scheduling eventually will become a problem. So this model is simple, efficient, but it relies on the developers cooperating between each other. A single misbehaving process could freeze the entire system. So modern operating systems rely on something called as preemptive scheduling. Cooperation doesn't work, but we have something called as a preemptive scheduling. A hardware timer periodically interrupts the running process, returning control back to the OS. So if I give the execution to the clock, the clock application is not going to have access to the CPU forever. it starts executing its instructions, and now a hardware interrupt is generated. The CPU is going to be given back to the OS process or whatever is the scheduler that's running. Now the OS has a chance to decide whether to give the CPU processing back to the clock or give it to the browser or maybe some other application. Thus, the scheduler can then decide whether to resume that process or switch to another. So, preemption allows some amount of multitasking, and it also is some protection against buggy or malicious software. So, without it, modern operating systems would not be usable. If you had the entire CPU dedicated just for one application, then we wouldn't have such a rich multitasking operating system like Windows or Linux or any of those things. So let's look at what is the scheduler trying to optimize. So before choosing an algorithm on how I should allocate the CPU to different processes, let us say I am the operating system scheduler, I have an algorithm. I can choose which application gets how much CPU time, because every few seconds or microseconds the application that is running will get interrupted and control will be given back to the scheduler, the operating system. So I can use an algorithm to decide if I want to just give it processing one by one, or do I use some fancy algorithms. Let's look at that. So for that we need to understand what is the scheduler trying to optimize. So one of the goals is of course fairness. We want to be fair to every process, each process should receive a reasonable share of CPU time, and no process should be ignored or starved indefinitely. So fairness matters. Another goal is throughput. How much total work the system completes over time. So if I switch too much, I may not be giving enough time for each process, or if I give too much time to each process, the system may start feeling very laggy. And a third goal, that is latency, which we talked about. So all of these goals kind of conflict. If I try to make the system very responsive, which means I'm switching very fast, then the processes do not get enough time to complete their work. If I give them enough time, then the system may start appearing very laggy. Or if I try to prioritize important applications which are time sensitive, like the clock, then somebody else, like the browser, may not get enough time. So it's all a balance. The scheduler is trying to do a lot of work. So that's where algorithms come in. Algorithms are basically proven ways of solving this particular problem along with its techniques and data. So early scheduling algorithms made these trade-offs very explicit. So there was things like first come first served, so where the scheduler basically says that if I have 10 applications waiting to be run, first come first serve. Whoever comes in first, I give them priority to execute a fixed amount of instructions, then I switch to the second process, then I switch, and I go on like that. There was also other algorithms like shortest job first. If I know that there is a job which is just trying to update the minute hand, the clock just wants to do the minute hand update and come back. Shortest job first, that is also a possibility. But then in practice, the OS cannot reliably predict how long a process will run, right? The clock may take much longer to update it. So round robin is something that generally works. It assigns each process a fixed time slice and cycles through all of them one by one. It improves the fairness, responsiveness, all of those things. But the too large or too small processes, they get different kinds of time slices. What I mean by that is if you have 10 applications and all of them, if you are going through them round robin, an application which is very quick will just get a few ticks of the CPU. An application which is much larger will get more ticks of the CPU because it's going to be scheduled more often in a round robin fashion, whereas the first one is already completed. So these algorithms teach an important lesson. Scheduling is always a trade-off. So let's look at why modern systems need more than just these algorithms like round robin, first come first serve, or any of these things. So classic schedulers, they assume a very simple condition, that there is a single CPU and workloads are uniform. That is not true. If you are running a browser, some pages might be heavy. If I'm running a video editor, streaming, if I'm doing a lot of I/O, they may be much more heavier. Or if I'm doing a simple clock which relies entirely on hardware interrupts to keep track of time, so that could be much lighter. So modern scheduling came up with the idea of CFS, or completely fair scheduling. It is pretty simple. So the process that has received the least CPU time should run next. So if I have 10 applications, one of them is very efficient. It is not taking much time at all to do its job and release it. So as a particular clock application, if it takes only 5 or 10 ticks of the CPU, whereas all the others have taken hundreds, my or this particular scheduling algorithm will try to give the CPU time to the process which has used the least number of CPU ticks. So instead of fixed time slices, the scheduler tracks how much CPU time each process has accumulated using a metric called virtual runtime. So this also kind of incentivizes applications to be very efficient. So the more efficient you are, the less CPU ticks you use, there is a higher chance that you will be scheduled again, you will be given more CPU to do your work. So processes that run more accumulate virtual runtime faster. Processes that kind of stay behind for whatever reason, they don't have much CPU time accumulated, so they will be scheduled immediately. So this is the kind of fairness we are trying to bring into scheduling. So at each scheduling decision, the OS picks the process with the smallest virtual runtime, allowing it to catch up. So the interactive tasks benefit naturally because they frequently block. If I'm trying to show, I'll take this simplistic example of a browser which is rendering a page. After the page has rendered, I really don't have anything to do because the user is going to read through some of it and then maybe move the mouse or then do something. So I can release my resources, which is my CPU time, or I can suspend myself. So that's how, as a browser process, I can save the CPU ticks and I accumulate less virtual runtime. So next time when the scheduling time comes around, the scheduler sees that, oh, this guy has used very less CPU, let me give him some more CPU time. So that way I keep getting back CPU. So it's like it's a carrot and stick approach. So we incentivize the developers to be as efficient as possible with the CPU ticks, and at the same time they also get more CPU time. It kind of sounds contradictory, but think about it, it makes perfect sense. That is what CFS is all about. So scheduling is a design philosophy. CPU scheduling is not just some algorithm, it reflects how an operating system values fairness, user experience, efficiency, all of those things. So the early scheduler answers questions such as, should interactive tasks feel instant? If there is a GUI activity going on, if somebody is moving the mouse, should I give him maximum priority? Or should background work be slowed to preserve responsiveness? For example, if I have a print spooler, do I just slow it down because it's going to do a bad job, or it's going to do a job, it's going to take its own sweet time? Maybe I just give it less CPU. That was the early scheduler thought process. But today we have much more advanced scheduling algorithms. I talked about round robin, I touched upon shortest job first, and we also talked about CFS. There is much more to be done in the operating system design. You can probably refer to some of the reference books which will give you a lot more details. But this episode gives you an idea of what scheduling is and why it is actually difficult to choose a good scheduling algorithm. So when a system feels smooth and responsive, it is rarely because the CPU is idle. If you see that your system is very responsive, it's not because the CPU is idle. It is because the scheduler is kind of balancing competing demands. It's maintaining that illusion of parallelism. So that's the short topic I wanted to cover in this episode. So CPU scheduling demands its own standalone episode. That's why this is a very short one. So go think about it. In the next episode, we'll be looking at how operating system extend this illusion into memory management by making every process believe that it has the entire machine to itself. So it's all pretty interesting. I hope you're enjoying these episodes. Drop some comments down there. If you like the episode, click on the subscribe button and do come back for more. Thank you for watching.